Good morning.
Good morning, sir.
Good morning, sir.
Good morning. Good morning. ಇವಾಗ ಎಚ್ಚೆತ್ಕೊಂಡ್ರ ಎಲ್ಲಾರು ವಾಟ್ ಅಬೌಟ್ ಅದರ್ಸ್ ಮಣಿ ಮಣಿ
Sir,
ವೆಲ್ಕಮ್ ಮ್ಯಾಮ್ ಆಫ್ಟರ್ ಲಾಂಗ್ ಗ್ಯಾಪ್ ವೈ ವಾಟ್ಸ್ ಅ ಪ್ರಾಬ್ಲಮ್ after a long gap you are attending a class.
sir.
Okay, back here with the IoT lesson. Now, in this particular Saturday session, as you know that we will go with an activity class and we'll see how the IoT projects are ruling different fields in a world, and next how the IoT projects is going to be there in a coming years and all. So Saturdays, usually Friday, I'll start doing this particular research, entering into the Google and YouTube and all the videos, whatever is there, viewing that and all the things. So when we will be, and always while we are teaching and all, assume IoT projects are like this. When practical, when I did a last unit, there in that particular unit, the real-time constraints we have seen that if it is a long field, how a communication can be done. Or assume that if assume 1 kilometer like that, the field is there, and so surrounding that you have to do a communication, and in one particular point in a farmhouse like that, or in any one particular point internet is there. Until internet, how you are going to communicate from that particular device? So when this particular concept will come into the mind, for example, in a Wi-Fi, for example, we are using Arduino boards, we are using Raspberry Pi, and all these particular things we are using. And we know that we need an internet to connect and to pass the data. When on this particular issues, when I am doing a research, I have observed many things that how a communication can be done, and many others are finding a solution for this, and they have achieved a different projects on this particular issues. That is, for example, I'll tell you like this. ESP8266, which we have used and have shown you also many times. And if you want, you can see again. So this is a one particular small board which we have seen that, and so this is there an ESP8266, and we can through Wi-Fi giving an username and a password, and then we can connect to internet. That is there, as you correct. So can I communicate with another ESP model without internet? That's question arises always. That is, anyway, Wi-Fi is there in a ESP8266. So from one ESP to another ESP, can I communicate? From there, I can communicate to another ESP, and there I can communicate to another ESP. Finally, one ESP will be there which is connected to the internet. So my data from this ESP, which is there far away, through other ESPs communicating, can I transfer a data which is far away where the internet is there? Of 1 kilometers, 2 kilometers, like that. Can we do this? So this doubt arises always, and I started searching in Google, in YouTube, and all. Finally, I got one particular beautiful small project. How to communicate with two ESP8266 models. How you can communicate. So with that particular inspiration, means I collected that particular video link information, and I want to show this to my children. Let them also see this particular video, and we'll start with today's session with that particular video. Coming to the thing here, just 1 minute. Yeah, just 1 minute. I will go with here, present, tab, ESP to ESP8266 data transfer using web client server architecture. I think now,
to ESP8266 to send data from one to another. We're going to configure one as an access point to run a web server and another as a client to collect temperature data and send it to the server. Alright, let's do this. This video is sponsored by Skillshare. Skillshare is an online learning community for creators with more than 27,000 classes in design, business, web programming, and other categories. In a few of my videos, you've seen me use JavaScript, HTML, CSS, and other web design technologies that you can easily learn using Skillshare. The first 500 of my subscribers can use the link in the description and get a 2-month free subscription to try things out. We're going to start by creating a new file. It will contain the code for the server and access point part of the project. The first thing we'll do is include both the Wi-Fi and the web server libraries for the ESP8266. Next, we'll define the variables that we're going to need for configuring the access point, namely the SSID, the password, the IP address, the gateway, and the subnet that the access point is going to have. All these parameters are arbitrary and you can set them up however you want. We'll create an instance of the ESP8266 web server class so that we can set up the web server. And for the temperature data that we're going to be collecting with the client, on the server side, we'll need a global variable that I'll name sensor value. In the setup function, the first thing we'll do is create the access point. We'll switch the mode to Wi-Fi AP. We'll use the sofap config method of the Wi-Fi object with the variables we defined earlier to configure it. And we'll use the sofap method to actually start the access point. The IP address of the access point will be the one we defined. However, as a sanity check, I'll just print it out on the serial monitor so that we can see that things are actually working. After the access point is running, we'll use a couple of routes to handle the traffic from clients onto the web server. The first one is just the top root path and will serve a very simple index page. I'll use a function that I'll name handleIndex. When the top root path is accessed, we'll simply send back the latest measurement that's been reported. That means that we need to make a request each time we want to see the latest measurement. The other route I'll call update. When that route is accessed, it'll call a function that I'll name handleUpdate. In that function, I'll simply update the sensor value as reported by the client. We can do this in different ways. I'll choose what I think is the simplest one, which is getting the value from a URL parameter. We'll use the arg method of the server object and look for a parameter named value that will convert to a float from a string. I'll print it out on the serial monitor, and I'll send a message back to the client to say that the value has been updated. We'll finish up by calling the handle client method inside the loop function and the begin method inside the setup function. I'll save the file onto my desktop, and I'll simply create a new folder called ESP8266 server client, and this is the server side of the project, so I'll simply call the file server. We can go ahead and test things out. I'll go ahead and connect the Node MCU board, which I'll use as the server, to USB. Make sure that the USB drivers are installed as we've done in other videos. I'll select the board and the port from the Tools menu and upload the code. I'll then go onto my Wi-Fi connections and see that the access point is available. I'll connect to it, and once the connection is established, I'll go to the IP address that I defined for the access point. As we haven't updated it, we get the initial value displayed on the page. I'll open a new tab and use the route update with a URL argument named value with an actual value of 28.3, and see that if I refresh the top root path, I'll get that new value. With the server side done, I can go ahead and open a new file for the client. I'll save it inside the same directory and call it client. On the client side, we'll only need the ESP8266 Wi-Fi library. We'll use a couple of variables for holding the values that we're going to read from the TMP36 sensor, and of course we'll need the variables to hold the SSID password and IP address of the access point we just created. We'll also need an instance of the Wi-Fi client class in order to send the data to the server. I'll configure the sensor pin as an input, but this is the default mode, so it's an optional step. It makes the code a little bit easier to understand. I can then connect to the access point as we've done in other videos. In this case, we'll use the SSID and password of the one we just created. I'll print out the IP address, which will be assigned by the access point. Next, we'll get a measurement from the TMP36 sensor. We'll use the analog read function to get a digital value from 0 to 1023. We'll multiply it to convert it to volts by 3.3 and divide by 1024. And then we'll use the data sheet of the sensor to convert that volt value onto an actual measurement of temperature in degrees centigrade. I'll print it out to the serial monitor to ensure that things are working properly. Now, to send the value to the server, we'll use the client object. First, with the connect method of the class, we'll connect to the IP address of the access point. We'll then create a request to the update route with the URL parameter value and the value we just got from the sensor. We'll use the print method of the Wi-Fi client class to send a GET request to that route with the URL parameter. We'll configure a couple of other parameters of the header of that HTTP request. We'll delay for a short amount of time, and then we'll print out the response from the server. We're ready to test things out. For the client, I'll be using the Wemos D1 Mini development board for the ESP8266. The connections of the TMP36 sensor are pretty straightforward. The data pin, I'll connect to pin A0, which is the only analog input pin on the ESP8266. The power pin, I'll connect to 3.3 volts, and the ground pin to ground. With these connections made, I'll go ahead and connect it to USB And once again, remembering to install the USB drivers as we've done in other videos, I'll select the corresponding board and the corresponding port for this specific board. I can tell which board is which because they use different USB to serial chips which are named differently in the Arduino IDE. I'll upload the code, I'll open up the serial monitor, see what value is being measured, and refresh the page to create a new request to the server. Indeed, I see that the value that was reported is displayed on the page. Because we're performing the measurement inside the setup function, it only runs once. And the reason for that is because I wanted to show you how to use the deep sleep method in order to have the board go to a low power mode in between measurements. So if we go back to the IDE, we can define a variable that'll hold the value in seconds of how long we're going to sleep for in between measurements. For now, I'll simply use 2 seconds, but this can be the time that you actually need in order to save battery in case the board is running on battery power. The only thing I'll need is to call the deep sleep method of the ESP built-in object with the time for which I want the board to go to sleep. I'll then connect a wire from the pin D0 to reset so that the board can reset itself once it comes out of the deep sleep mode. We'll let it run a few times, and if I go back to the website, I can refresh and see the new value being updated. And if I mess around with the sensor, put my finger on it, I can increase the values and refresh the page to see these new values being reported. And that's it. We've learned how to use the Wi-Fi client and the Wi-Fi server classes in order to send data from one ESP8266 to another. If you like my videos, I invite you to my Patreon page where you can chip in a buck or two. That really helps me put in more time into the videos and release them quicker. But whatever you do, don't forget to like, subscribe, or leave me a comment. You can also interact with me on social media. I'm on Instagram, Twitter, and Facebook, and you can even use the community tab of the channel. Thank you for watching my videos, and I will see you next time.
Yeah. Now you have seen that particular video. In that particular video, we have seen that how they are using an ESP8266 and how they are making one as a server and another one as a client and using a server client architecture means the coding how we have did the server socket and the client socket in the Python programming or maybe in the networks programming. It's the same concept they have used here and they started the communication. That is, now we what you have to observe in this particular project. The project, what you have to observe is here no internet is there. That means that the data can be transferred from one to another with the IP address identification. So that is there. So that is here there is no rule like that. For the same IP address I have to give. No, whatever IP address you have designed means you have taken for that particular access which you have to make in a server. So for that will become a gateway IP address for you and another IP address which you have seen in a video. So that will be in a client IP address. So client will always communicates with the server and the response will be there from a server also. Any doubts and you want to discuss on this particular video, it's open for discussion now. Anybody wants to discuss on this particular video? Anybody? Now we'll step on to the next particular communication system. Okay, now this is a fact. What is the disadvantage in this particular way of communication? If assume that there is a forest project which we are doing and a big farming land project which we are doing, and no internet is there in that particular locality around, you can say like this, for 10 to 15 kilometers. And how I can connect now to internet. Now for every maximum your Wi-Fi will works with an 100 to 200 meters. That is every 200 meters, putting one ESP8266 isn't a problem, especially within a power maintenance of that particular board. Lot of problems will be there in that particular regard. Then how we can make a connection. So in that particular sense, when I searched, keeping this concept into a mind that I want to communicate far within a more than some 4 to 5 kilometers away without internet, assume, and afterwards I want to connect to the internet. And then LoRa came to my mind. So I have heard always theoretical concept of an LoRa, that how this particular long range antennas will work. So in that means that the WAN setup, how it will be there, wide area network. Can we implement this? Any projects has been done on this particular using LoRa, how we can do this. So a lot of means this type of an questions arised in my mind. So when I digged based on this particular questions, I digged in Google and YouTube. I got a lot of videos. In that one interesting video, which practically they have implemented a project where around some 10 to 15 kilometers no internet is there, and they are communicating from one LoRa lax model to another one model, and then finally they are connecting to an internet from that particular point. So this thing have observed, and it's very nice video how they have did that particular project, and they have even told that these components where you are going to get this type of an components, either in Amazon also you can get, and eBay also you can get, and you can go on the websites, and lot of support they have told different websites and PCB even boards, how if I give one particular scenario of a problem, how I can get a PCB board for that. So all these details they have recorded in a video very well, and have seen it. And I will share that particular video with you also. Now you observe that's particular video, and we'll see how a LoRa model can be put into the Node MCU or an Arduino board, and how we can make a project out of that particular thing, and we can solve our problem that without internet, how we can pass data in a kilometer wise. Just a minute. No, just a minute. Now I want to share that particular video tab.
You will learn how to make an IoT smart irrigation system using Node MCU ESP8266 Wi-Fi module, 15-kilometer LoRa transceiver modules, Arduino Nano, and a capacitive soil moisture sensor V1.2. This area is around 6 kilometers from my friend's house. Currently in this area, No GPRS signals are received, and as per my friend's demand, he wants to monitor the soil moisture on his cell phone. As no internet is available in this area, so we cannot use any internet supported devices like the Node MCU, ESP8266 or ESP32 modules on the transmitter side. So due to the 6 kilometers long distance, we will have to use long range radio frequency modules. The PCB boards used in this project are sponsored by the PCBWay company. PCBWay is quite professional in the field of PCB manufacturing. You can try their services at extremely low prices, only $5 for 10 PCBs and
Just have a look on that particular website after this session and all. Whenever you're feeling a free, so PCB way, you go, you open it, and you just navigate to the different tabs, how what they are provided, and all. Definitely, you will get a lot of information on regarding a PCB and all. So how even a node MCU board you can make and how with sensors you can make a fit to that and according to your project how you can make a small board which will be adjustable. That all information is there in that particular website. So then we'll
$30 in total for 20 PCBs assembly. Besides this, the new members also get a $5 bonus. The Gerber files of the PCB boards used in this project can be downloaded from the PCBWay official website. You can find a link in the description. Thanks to the REX Technologies for making such an amazing long-range 15-kilometer transceiver modules. On the transmitter side, LoRa module is used with the Arduino Nano to send the sensor's data to the receiver. On the receiver side, the LoRa module is connected with the Node MCU ESP826655 module. At this point, you can directly connect the Node MCU module with the laptop and monitor the data on the serial monitor, or you can design a cell phone application and monitor the data from anywhere around the world. For the demonstration purposes, I connected a variable resistor. I can monitor the values in real time. Notification messages are sent when the sensor value increases above or decreases below a certain predefined value. These values are sent from the transmitter side through a 15-kilometer LoRa transceiver module. On the receiver side, another 15-kilometer LoRa transceiver module is connected with the Node MCU ESP826655 module, which receives the data and then sends it to the Blink application. After performing all the basic tests, finally I soldered all the components on the Vero board and fixed the transmitter side in a waterproof plastic enclosure. The capacitive soil moisture sensor was working great. There was no disconnection and I was able to receive the moisture values in real time. The type of the capacitive soil moisture sensor I used was later damaged due to the exposed electronic components. That's why I ordered another capacitive soil moisture sensor which is completely waterproofed. I have been testing this IoT smart irrigation system and is working perfectly without any problem. The REX LoRa module pinout, technical specifications, basic programming, interfacing and AD commands are already explained in my previous tutorials. If you are using the REX RYLR890 based LoRa module for the first time, then I highly recommend first watch my previous tutorials which covers the extreme basics and then you can resume from here. I will provide links in the description. In this tutorial we will cover number 1. Transmitter and receiver circuit diagrams. Number 2. Transmitter and receiver side programming, and finally number 3, testing. Without any further delay, let's get started.
Whenever you listen to a pitch of a startup, they claim at the end of the pitch, and we are going to change the world with this technology. I think among all the startups that claim to change the world, Arduino changed the world already.
There is a company who's launched our boards in space, and they are doing experiments in the International Space Station. So you can
The components and tools used in this project can be purchased from Amazon and Banggood. The components purchase links are given in the description. These are the long-range wireless 915 MHz radio frequency LoRa transceiver modules by the REX technology. As you can see, this transceiver module has a total of 6 pins which are clearly labeled as VDD, NRST, which is the reset pin active low, RXD, TXD. Pin number 5 is not used, while pin number 6 is the ground. This is a soil moisture sensor which measures soil moisture levels by capacitive sensing rather than resistive sensing like other sensors on the market. This capacitive sensor by the DF robot is made of corrosion resistant material which gives it an excellent service life. The capacitive soil moisture sensor is used just like the resistive soil moisture. Simply insert it in the soil around your plants and make an amazing, low-cost, real-time soil moisture monitoring system. This module includes an onboard voltage regulator which gives it an operating voltage range of 3.3 to 5.5 volts. It is perfect for low voltage microcontrollers, both 3.3 volts and 5 volts. As you know, Arduino Nano is based on the 5-volt controller, while the LoRa transceiver module by the REX technology can handle voltages from 2.8 to maximum 3.6 volts. The typical voltage is 3.3 volts as per the datasheet. From this information, we know that this module cannot be directly interfaced with the Arduino. For this, we will need some kind of converter which can convert 5 volts into 3.3 volts. But instead of using the converter, we can use a simple voltage divider circuit. As you can see, 4.7K and 10K resistors are connected in series, which gives me 3.4 volts, which is perfect for the REX LoRa transceiver module. A wire from the middle of these resistors is connected with the RXD pin of the LoRa module. The other leg of the 10K resistor is connected with the ground, while the other leg of the 4.7K resistor is connected with the TX of the Arduino Nano. The RX pin of the Arduino Nano is connected with the TXT pin of the LoRa module. The ground of the LoRa module is connected with the ground of the Arduino Nano. If you want to use the Arduino Uno, you can still follow the same exact connections. The ground and VCC pins of the capacitive soil moisture sensor are connected with the ground and 5-volt pins of the Arduino Nano, while the analog output pin of the capacitive soil moisture sensor is connected with the analog pin A1 of the Arduino Nano. Now let's have a look at the receiver circuit diagram. The IoT Smart Irrigation System receiver circuit is based on the Node MCU ESP826655 module and 15 km transceiver module by the REX technology. So first let's start with the 5-volt regulated power supply based on the LM7805 voltage regulator. The positive and ground pins of the DC female power jack are connected with the input and middle legs of the 7805 voltage regulator. Two 470 microfarad capacitors are connected at the input and output sides of the voltage regulator. A 330 ohm resistor is connected in series with a 2.5 volt LED. This is a current limiting resistor. A wire from the output of the voltage regulator is connected with the VN pin of the Node MCU ESP826655 module, while the ground of the power supply is connected with the ground pin of the Node MCU module. The 15 km LoRa transceiver module interfacing with the Node MCU ESP826655 module is very simple. While interfacing LoRa transceiver module with the Node MCU ESP8266 You don't need any voltage converter or a voltage divider. You can start by simply connecting the VDD and ground with the Node MCU module 3.3 volt and ground pins, while the TX pin of the LoRa module is connected with the RX pin of the Node MCU ESP8266, and the RX pin of the LoRa module is connected with the TX pin of the Node MCU module. So that's all about the transmitter and receiver circuit diagrams. For the easy interfacing, I designed PCB boards for the REX LoRa module and Node MCU ESP8266 Wi-Fi module. These PCB boards are manufactured by the PCBA company. As you can see, the quality is really great. The silk screen is quite clear and the blue and black solder mask looks amazing. I'm 100% satisfied with their work. I completed the soldering very carefully, and in the end I tested all the connections and luckily there were no short circuits. Finally, I connected everything as per the circuit diagram already explained. Now let's make the playing application. Follow the same exact steps and enjoy the music.
What makes me a regular customer of Country Delight is the consistency, the regularity of the quality which they are maintaining. It is at par. Even if the weather is 45 degrees Celsius, I'm not finding any thing bad in the milk.
The IoT Smart Irrigation System project is based on two programs. One program is written for the transmitter side while the other program is written for the receiver side. Let's first start with the transmitter side programming. I started off by defining a pin for the capacitive soil moisture sensor. The analog output pin of the moisture sensor is connected with the Arduino's analog pin A1. I also defined a variable of the type integer for storing the moisture sensor value. Then I defined two variables, data underscore length and sensor data of the type integers. Inside the white setup function, I activated the serial communication and selected 11,000 and 5200 as the baud rate. And finally, set the capacitive soil moisture sensor as the input using the pin mode function. Inside the while loop function, we have only two user-defined functions, which are the multiple sensors and send underscore data functions. The multiple sensors function is used to read the capacitive soil moisture sensor and to make a complete string message using %sign as the delimiter and to find the data length. While the send underscore data function is used to send the complete message consisting of the data length and the sensor value. So that's all about the transmitter programming. Now let's have a look at the receiver programming. On the receiver side, before you start the programming, first of all make sure you download all the necessary libraries from our website electronicclinic.com. You can find a link in the description. This is the authentication code which was sent while making the Blink application. I simply copied and pasted over here. This is the name of the Wi-Fi router and this is the password. I defined a timer, some variables of the type string, character and integer. I also defined a pin for the relay and a flag to stop the unnecessary repetition of code. As usual inside the white function, I activated the serial communication, set the relay as the output. Blink.begin function takes three arguments as the input, the authorization code, the SSID and the password. Sensor value 1 and receive data are two user-defined functions which are executed after every 1 second. Inside the while loop function, we have only two functions which are the blink.run and timer.run functions. Receive data function is a user-defined function. It has no return type and does not take any arguments as the input. The purpose of this function is to check if the Arduino has received any data from the LoRa module. Split the entire string message. The different parameters are stored in different variables. Finally, the capacity of soil moisture sensor value is stored in a variable q, which is of the type string, which is then converted into integer. The following conditions check the sensor value received from the transmitter and turn on and turn off the relay connected with the 0 pin of the NodeMCU module. Currently, I'm using 20 and 30 as the predefined values. You can change these values as per your requirement. The purpose of the relay if is to stop the unnecessary repetition of code. Sensor value 1 is also a user-defined function. It has no return type and does not take any arguments as the input. The purpose of this function is to send the capacitive soil moisture sensor value to the Blink application gauge widget. These two conditions are used to send the notification messages as the soil moisture decreases or increases above the predefined values. Finally, the get value function is used to split the string message using any character as the delimiter. So that's all about the programming. The circuit diagrams, programs and libraries can be downloaded from our website electronicclinic.com. You can find a link in the description. Support me on Patreon for more videos. I hope you liked today's episode. Like and share this video with your friends. See you in next episode and thanks for watching.
Yeah, you have seen now this particular video how a LoRa will can be connected within a 15 kilometers range from one LoRa module to the another LoRa module. In our next hour, I will only take the class and we'll go for the next videos and we'll see how even a LoRa is best for another different projects and all. Okay, just take a break. After a break, I will come back and I will again go with a third hour class also. Thank you.